Hello guys, my name is Bintang. I'm with my friend here, Roger. Roger, say hi.
Hello.
Hello. Today we're going to talk about LU decomposition. What is LU decomposition? Uh, LU decomposition basically is a process that factors a matrix as the product of a lower triangular matrix and an upper triangular matrix. The product sometimes include permutation matrix as well. LU decomposition can be viewed as the matrix form of Gaussian elimination. And up here, you can see an example of the final form of LU decomposition. When given the matrix A, LU decomposition is to find a matrix L and matrix U such that matrix A equals matrix L times matrix U, where L is a lower triangular matrix with ones in the diagonal, and U is an upper triangular matrix. It is easy to remember since L stands for lower and U stands for upper. There are also specifications such as matrix A must be able to be reduced into row echelon form, which is matrix U, without using any row swap. And L and U are not unique. What are its application? Roger, time is yours.
All right. So LUL decomposition might come in handy when we are trying to find the determinant of a matrix. Since our matrix are now decomposed into both a lower and upper triangular matrix, finding the determinant of a triangular matrix is just the multiplication of its diagonal elements, as we can see from the highlighted elements in the lower and upper triangular matrix below. By doing so, then the determinant of the matrix can be calculated as a determinant of A equals to determinant of L times determinant of U. Next slide, please. Another application of LU decomposition is to solve a linear system. So given a linear system AX equals to B, we can use LU decomposition to solve the set. First, we are going to decompose A into L times U, as shown in the equation, the first equation in this page. Then we are going to group together U times X and compare the matrix L, the lower matrix, with our value B. By comparing the triangular matrix L to the matrix B, we can use forward substitution to find a middleware matrix Y, which we can then use to compare with our group UX above to find the X matrix easier by using back substitution this time. Other application of LU decomposition include machine learning, linear regression, image processing, computer graphics, but we will not dive into those topics this time. So the next part will be example case. Going back to you, Bintang.
Okay, thank you, Brandon. We will look into the example cases. We will first learn how to find LU decomposition of a matrix. In short, the answer is using ERO. Since matrix U is the row echelon form of matrix A, we will use elementary row operation, except swapping rows, to transform A into U. And we'll take note of the operation we used and insert the opposite of the ERO multiplier into matrix L at the corresponding location for each operation. Okay, so now we are looking at this matrix A, which is 1, 4, minus 3, minus 2, 8, 5, 3, 4, 7. We will first try to turn the minus 2 in the second row into 0. And we can do that by adding 2 times row 1 into row 2. And we'll get 16 minus 1. Okay, very nice. And then next, we will turn the 3 into a 0 by adding minus 3 times R1 or row 1 into the third row. And then we will try to make the minus 8 into 0 by adding half times the second row into the third row. And after doing all this, we are finally be left with the upper triangular matrix version of A, which is equal to the U matrix. Okay. Now that we have the U matrix, we will look for the L matrix. We can look for the L matrix by looking at the multiplier of each elementary row operation and then putting in the reverse of that multiplier into the template L matrix at the corresponding location for each operation. So for instance, the first ER row that we perform is to add 2 times the first row into the second row. And we take the 2 and we reverse that to -2 and add that to the corresponding position, which is indicated by the red square. We do that for each ER row and we will end up with a fully filled L matrix, which you can see on the left, with ones running through the diagonals and the filled in values on the lower triangular side. And this will result in us having both the U matrix and the L matrix, which is the final result of the LU decomposition. Back to you, Roger.
All right, so the next part will be proving what Bintang has shown previously in MATLAB. Next slide, please. So the first example will be using a step-by-step operation to obtain our L and U matrix. So as usual, we'll start by clearing out the previous output in the terminal by using the first 3 lines of the code, the clear all, close all, and CLC. And then we'll create our matrix A with the given matrix 1, 4, -3, -2, 8, 5, 3, 4, and 7. Our matrix A will be reduced into matrix U later on. So we'll have to create another matrix L, which will be used for the lower triangular matrix with the diagonal value of 1, 1, 1, as shown at the code at line 13. So using Gauss elimination, like just now, we are going to reduce matrix A. We are storing the index of K, the multiplier, into the index inside matrix L. So the first operation is by using the multiplier 2. So we will inverse that value. So K equals to -2 this time. We will reduce the matrix A at row 2 while storing the value of K -2 inside the second row and first column of the lower triangular matrix. So by doing each of this operation for each of the index, we are going to arrive at our L and U matrix as shown when we are printing the L and U matrix in the code below. So we should arrive with the same matrix as what Bintang shown previously. To prove that these two matrix is equal to A, we can just times both matrix together, as shown in the right side of the command window, right? So L times U is equals back to A. Next slide, please. Here is an example algorithm showcasing the loops required to make the algorithm, the step-by-step that we do just now, but this time it's automated. So our algorithm is called a Doolittle's algorithm. It was the reference can be found on the commented link at the code up there. So we just fit A into the function, and it should output L and U, our lower and upper matrix, same as what we arrived at just now, but this time it's automated. Next slide, please. MATLAB also have a built-in function where you can call decomposition by using the command lu. The most common output for this function can be stored into 2 different arrays, L and U, but we can see that the lower and upper triangular matrix is different from what we obtained previously, right? So this is because MATLAB doesn't follow the Doolittle's algorithm while solving decomposition, which proves back to what Bintang said initially. L and U are not unique, and there might be permutation when it comes to LU decomposition. And next slide, please. And thank you. That will be the end of our presentation.
Okay, we will stop the recording.